The James Webb Space Telescope JWST has made a discovery that has captivated scientists and observers alike in its ongoing exploration of the cosmos. The telescope has recorded intriguing visual data, glowing lights that seem to originate from a concentrated point in space resembling the illumination pattern of a city seen from above at night. What makes this observation even more compelling is its source. A region roughly 4 light-years away, this mysterious display of light has reignited public and scientific curiosity about the possibility of intelligent life beyond Earth. Has specifically directed renewed attention to Proxima Centauri, be the closest known exoplanet to our solar system, which is situated in the habitable zone of its host star Proxima Centauri. The telescope's powerful sensors captured these radiant flashes emanating from the exoplanet, leading to a flurry of speculation and hypothesis. Could these lights be artificial in origin? Might they represent technological activity or even signs of an advanced civilization? Such questions, though speculative, are not unfounded. The human fascination with life beyond Earth is not a recent development. It spans centuries and has been intensified by each new scientific advance that expands our understanding of the universe. Whenever new data hints at the possibility of life outside Earth, it is received with widespread excitement and cautious optimism. Pivotal moment in this ongoing inquiry came with the deployment and activation of the James Webb Space Telescope, which began operations in 2022 with its unprecedented infrared sensitivity and ability to peer deeper into space than any previous instrument. Webb has enabled scientists to detect signals and patterns that were once beyond the reach of even the most advanced observer. During its examination of Proxima Centauri, the telescope recorded unusual thermal and light-based anomalies, patterns that mimic those produced by large-scale artificial lighting. This raised a bold question among researchers. Could this be the distant glimmer of an extraterrestrial city? Such an idea, while still hypothetical, has drawn the attention of scientists across disciplines. The concept that intelligent life might exist on Proxima Centauri b, and that it might be capable of building cities or other large-scale structures, is both astonishing and tantalizing. If verified, it would mark one of the most significant scientific discoveries in history. Researchers speculate that this could represent a form of energy usage or infrastructure that, while alien in origin, follows principles that are not entirely unfamiliar, possibly even resembling our own methods of urban illumination, albeit shaped by a completely different planetary environment and evolutionary history. Scientists such as David Kipping, an astronomer at Columbia University, have pointed out the complexity of Proxima b's environmental conditions. Unlike many rocky planets that simply absorb light from their parent stars and emit it as infrared radiation, Proxima b exhibits a unique energy signature. This is likely due to its intricate orbital and thermal relationship with Proxima Centauri, a red dwarf star known for its flaring behavior and strong magnetic activity. These features make Proxima b a particularly fascinating candidate for further study. One of the most notable advantages of the James Webb Space Telescope is its capacity to detect infrared light, which is invisible to the human eye but carries a wealth of information about an object's temperature and composition. This capability allowed the telescope to detect variations in Proxima b's infrared emissions, especially during its nighttime phase, when any artificial illumination would stand out against the cold, dark backdrop of space. The JWST's instruments are sensitive enough to capture even faint glimmers that many other telescopes would miss, making it an ideal tool for evaluating whether the lights observed could be of non-natural origin. Proxima Centauri b maintains a close orbit around its host star, completing one revolution every 11.2 Earth days. This tight orbital path results in significant differences in the planet's exposure to stellar radiation as it rotates. Proxima b undergoes a cycle of day and night similar in concept to Earth's, though with more extreme temperature variations. If the planet lacks a dense atmosphere or oceans to moderate its climate, the day side could become intensely hot, while the night side might plunge to freezing temperatures. These drastic fluctuations are of particular interest to scientists, as they can reveal clues about the planet's atmospheric composition or lack thereof. Without an atmosphere to trap heat or distribute it evenly across the planet's surface, Proxima b would likely exhibit extreme thermal contrasts. By observing these variations in temperature, the James Webb Telescope can infer details about the planet's surface and atmospheric dynamics. Its unique orbit around Earth combined with its observation schedule allows researchers to monitor Proxima b with remarkable consistency, enabling long-term studies of its thermal behavior and atmospheric evolution. If an atmosphere is present on Proxima b, the next step in analysis is to determine its chemical composition. Scientists hope to detect biosignature gases, chemical markers such as oxygen, methane, and water vapor that are commonly associated with biological activity on Earth. These molecules, if found in the right ratios, would suggest the possibility of life-supporting conditions. To identify these elements, scientists must analyze the star light that filters through the planet's atmosphere during transits, an extremely complex and delicate procedure, though the James Webb Telescope is optimized for detecting elements such as carbon dioxide, water vapor, and methane. It is less suited for identifying free oxygen, which is considered a critical marker for biological activity. However, it can also detect ozone, a secondary indicator of oxygen-rich atmospheres. These measurements could help scientists determine whether the planet's atmospheric chemistry is shaped by geological activity alone, or if it includes potential signatures of biological processes. As we await more definitive evidence, it's important to recognize that the JWST has observational limitations. Its reach is largely confined to the nearest exoplanets, making detailed studies of more distant worlds a challenge. For this reason, astronomers are looking forward to the arrival of next-generation telescopes, such as the extremely large telescope YLT-SET, to become operational in 2028. This powerful ground-based observatory will enable researchers to examine the atmospheric properties of distant planets in much greater detail, adding a vital tool to the search for life. In parallel with these efforts, scientists are also working on new technologies to improve our ability to detect and study exoplanets. One major challenge is the overwhelming brightness of stars, which often drowns out the faint reflected light from their orbiting planets. To overcome this, researchers are developing Cornus internal instruments that block out starlight within a telescope to allow dim planetary light to pass through by reshaping the light waves entering the telescope. Coronagraphs reduce glare and reveal faint objects that would otherwise remain hidden. Another groundbreaking innovation is the Star Sheet, a massive pedal-shaped spacecraft designed to fly in perfect alignment with a space telescope positioned tens of thousands of kilometers away. The star shade would block starlight before it even reaches the telescope, allowing only the light from nearby planets to enter the lens. This technique could significantly improve our ability to detect and study planets in the habitable zones of their stars where liquid water and perhaps life might exist. Despite the promise of these technologies, they require extraordinary precision and engineering. For example, a star shade must remain aligned to within fractions of a millimeter over vast distances to be effective. These devices also need to be compact enough for space travel, energy efficient, and capable of surviving the hostile conditions of outer space. Still, the potential scientific rewards are vast. Successfully analyzing the atmospheres for biosignatures could ultimately confirm the existence of extraterrestrial life, but in addition to detecting signs of life, scientists hope to one day directly image distant planets in detail. This would allow researchers not only to confirm their existence, but also to map their surfaces, identify geological features, and study their climates. Future telescopes may use adaptive optics to correct distortions caused by Earth's atmosphere, improving image clarity. These technological advancements, combined with light-blocking systems, will mark a significant leap in our ability to explore and understand alien worlds. The development of such space-based observatories represents a major stride forward in addressing one of humanity's most enduring questions: are we alone in the universe? As we continue refining our ability to observe distant solar systems, analyze their atmospheres, and interpret the data they yield, we may be on the verge of answering that question for the first time in human history. Discovering life, or even evidence of advanced civilizations, would redefine our understanding of existence and our place in the cosmos.